Welcome back. So we were continuing on regression examples on empty cars dataset. So as we know that given a different features of new prototype car, can you predict the mileage or the miles per gallon of the car? Now, the data that you have in your hand is some sort of, like this kind of typical table format that you have, and say maybe Mazda RX-4, which gives you 20 miles per gallon, 21 miles per gallon. It's a 6-cylinder car. It has a displacement of 160. It gives horsepower of 110 and weight is 2.62. So there could be another car, Hornet 4 Drive, which has a miles per gallon as 21.4 miles per gallon, and 6-cylinder car displacement is about 258 and horsepower 110, weight is 3.215. Now the prototype car that you have built, maybe it's only available in your computer models, has a 4-cylinder car. Displacement is 120, horsepower is 100, and weight is 3.2. Now you want to estimate what is the miles per gallon. So you want to predict or estimate the variable miles per gallon. So like any data science and project, what we will do, we will start with some visualization. So we take this weight, suppose you take this weight variable and the miles per gallon, and we plotted them. So what we are seeing that as the weight of the car increases, the miles per gallon decreases. So we see a negative relationship between the weight and the miles per gallon. So naturally, we would like to fit a straight line to begin with, miles per gallon as a function of beta naught plus beta 1 times weight plus some error. So that means there will be some error because you can see that there is some sort of randomness in the system, and so like this point we would like to have it on the straight line, but there is this not exactly there, so there will be this difference is the error. So for this point it's the error. Interestingly, this point is almost on the line, so error for this point will be almost 0. So there will be some point which will be on the line or very close to the line. For them the error will be 0, and then there will be some point here, some point here, some point here. For them some error will be there. Now if we consider a third variable, say displacement in our analysis, so the model will be beta naught plus beta 1 times weight plus beta 2 coefficient times displacement plus error. Now two things you must notice. First, in the previous case we had only two variables, weight and miles per gallon. So all the points were on the 2 dimension. Now we are bringing third variable, displacement. In this axis displacement, this is the weight, and this axis is miles per gallon. In this, so naturally all the points that we are seeing, they're in the 3 dimension. And so it's likely if you can imagine yourself, you are in a room, in one length is weight, x-axis is weight, y-axis is displacement, and the z-axis is miles per gallon. Then all these points are somewhere kind of hanging in the 3-dimension space. So this is what you are seeing in the graph. Now this model is trying to fit a plane through these points hanging in the 3D space. So previously it was a line in 2 dimensions space. The model was a line. In 3-dimension space it's a plane. Okay. So given a vector of inputs x1, x2, x3, now we are kind of putting in some kind of abstraction. We predict the output y. So y equal to beta naught plus x1 beta 1 plus x2 beta 2 plus x3 beta 3 plus epsilon. The term beta naught is the intercept. Often it is convenient to include a constant variable in the X matrices that includes the beta naught in the vector of coefficient beta, which is only the beta 1, beta 2, beta 3. So in these things. So we have data about now y and x, and we have a model. What we don't know, the value of these coefficients. So we want to estimate these parameters beta 1, beta 2, beta 3. Now we are going to expand this model to the p-many features. It's just you had a model, a 3-dimension model. Now you have a p-dimension model. So in 2 dimension, you were fitting a straight line. In 3 dimension, you were trying to fit a sort of a plane where in the p dimension, more than 3 dimension, we cannot visualize. So what we have to do, we can just, imagine that in a p dimension, it will fit a p minus 1 dimension hyperplane. So that is what exactly we are going to do. So why is this model is going to fit a p minus 1 dimensional hyperplane in a p-dimensional data space. So this is the exact same problem. We have bunch of x's, we have bunch of and a y. The given x and y's, we want to estimate the betas. So that is where the whole problem lies. Now, when it comes to estimation of beta, let us try to understand how the values of beta is going to affect my model. So let's take this line beta m naught as 35 and beta 1 is minus 5. So my model is MPG 35 minus 5 times weight plus epsilon. Now if I change it to 39 and minus 6, now the model is also changing. You can see. So there are only 2 data. One is 2 values that I'm considering for beta naught and beta 1, 35 and minus 5 and 39 and minus 6. And you can see the model is kind of, changing accordingly. Now, what are the choices of beta that can I have? So beta naught can take values around the say x-axis, and suppose beta 1 takes the values around this axis. So one possibility is beta naught is taking 35 and minus 5, so which is this value. Another possibility is beta naught is taking 39 and minus 6, so this is this value. And this gives us 2 possible lines. So the question is which one to choose. But one other question is, why should I choose between these 2 only? There could be infinitely many possible choice of line, and for each line I will get a different. Each choices of beta, I will get different choices of line. So which beta to choose? Each choice of beta will give me a line. Now question is which one to choose. So there comes an interesting concept called residual sum of squares of error, and from where the concept of least square comes. So we have the model y equal to x beta plus epsilon. Y is a n cross 1 vector, x is a n cross p matrix, beta is a p cross 1 vector, and epsilon is a n cross 1 vector. Now what we are going to do, we are going to understand the residual sum of squares of error. So y minus x beta, so we can just take the x beta on the left side, that gives us a y minus x beta, which is epsilon effectively. Transpose y minus x beta, effectively what is it? This is y minus xi transpose beta whole square and sum of that. Now this is nothing but epsilon I square or epsilon transpose epsilon. So this is called residual sum of squares of error. Now, if I plot this residual sum of squares against different choices of beta naught and beta 1, we get a valley like this kind of a valley. And of course, we would like to choose a beta naught and beta 1 somewhere in the valley which will give me the minimum sum of squares of error. And turns out its minimum always exists, and it may not be unique, but minimum always exists, and we will talk about it. But this we are going to talk about it, but let's talk about more about it. So how can we get this minimum? So easiest thing is you differentiate this residual sum of square with respect to beta and set it equal to 0. So what is my residual sum of squares of beta? Y minus x beta transpose times y minus x beta, and differentiate it with respect to beta and set it equal to 0. So after differentiating, what I have is minus 2x transpose times y minus x beta equals to 0. Now this we can write it as x transpose x beta equal to x transpose y. This set of equation is called normal equations, and x transpose x is a p cross p matrix. So the normal equations have p unknown and p equations. Now solving this equation, we can have beta hat equal to x transpose x inverse x transpose y, and this solution is called ordinary least square solution on OLS, or least square method provides an analytical solution. We have an exact analytical solution because you see that all we have to do, we have the data x. In the data, all we have x and y. You just plug in x and y in this formula. This will give you beta hat, and that's it. Your model is ready. You can plug it in this model. You can deploy it in a production setup. So we will stop here now, and we will do some hands-on to see how these things work. Thank you.